So let's talk about standard model of particle physics.
The standard model. It's like the grand framework of particle physics. In short, it catalogues all the known fundamental particles and three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. We've got quarks and leptons, the building blocks, and force carrying particles like photons and gluons. It doesn't cover gravity, that's for a future theory, but for the rest of the universe's particles and interactions, it's our best tested model so far. Where do you want to dive in?
So can we call it simply standard model or it's a standard model of particle physics? Why particle physics?
We call it the standard model of particle physics because it's specifically about the fundamental particles like quarks, electrons, neutrinos, and the forces between them. Physics covers a broad range of phenomena: mechanics, thermodynamics, cosmology. But when we say particle physics, we're talking about the smallest constituents of matter and energy and how they interact. So, standard model is shorthand, but adding of particle physics just makes it clear which part of the universe we're describing.
So energy and matter, how they interact, what do you mean by that? And what are the particles we have?
When we talk about how energy and matter interact, we mean that particles can exert forces on each other or even transform. For example, an electron might interact with a photon, a particle of light, or quarks might be held together by gluons. Now, the particles we have in the standard model fall into categories. There are fermions, which make up matter. These include quarks, like up and down quarks, and leptons, like the electron or neutrinos. Then we have bosons, which are force carriers, like the photon, electromagnetism, the W and Z bosons, weak force, and gluons, strong force. And of course, there's the Higgs boson, which gives particles mass.
So you call bosons. Is the meaning of W and Z? Bosons means a particle with integer spin.
Exactly. Bosons are particles that have integer spin, like 0, 1, or 2. In the case of the W and Z bosons, they have spin 1. These particular bosons are responsible for mediating the weak nuclear force, one of the fundamental forces. The W bosons, there's a W plus and a W minus, are involved when particles change type, like when a neutron turns into a proton. The Z boson is neutral and helps with processes where particles interact without changing type. Both are key to things like radioactive decay.
What do you mean by this radioactive decay part?
Radioactive decay is when unstable atomic nuclei transform into more stable ones. In that process, particles are emitted or transformed. The weak force, mediated by the W and Z bosons, is what allows certain particles inside the nucleus, like neutrons and protons, to change identity. For instance, a neutron can decay into a proton, an electron, and an antineutrino. Without the weak force and those bosons, processes like beta decay, which is a common type of radioactive decay, wouldn't happen.
So who proposed standard model of particle physics and what are the things he included there? Like which particles?
The standard model emerged through contributions from many physicists, but as a unified framework, it came together in the 1970s. Key contributors included Glashow, Weinberg, and Salam, who unified the electromagnetic and weak forces, the electroweak theory. The particles included are first the quarks, up, down, charm, strange, top, and bottom. These build protons, neutrons, and other composite particles. Next, the leptons, the electron, muon, tau, and their neutrinos. Then the force carriers, the photon electromagnetism, W and Z bosons weak force, and gluons strong force. Finally, the Higgs boson, which gives mass to particles. This set of particles covers all known matter and force interactions, except gravity, which still awaits unification.
So why do you call here unification part? Like, why they unify this theory?
They aimed for unification because nature tends to be simpler at a deeper level. Initially, electromagnetism and the weak force looked very different, but by unifying them into a single electroweak theory, they revealed that at high energies, these forces are actually just different aspects of one framework. This helps us understand the universe with fewer fundamental principles. The dream is to unify all forces, including gravity, into one grand theory, so that we see the whole picture of how the universe works at the most fundamental level.
Okay, the universe works at the most fundamental level. What do you mean by that part?
I mean that we're trying to uncover the deepest rules that govern everything, whether it's why particles have mass, how they interact, or how forces emerge. At the most fundamental level, we're not looking at everyday objects or even atoms, but the smallest building blocks, quarks, electrons, fundamental forces, and the laws that control them. If we fully understand those fundamental particles and forces, we have the bottom layer of reality. Everything bigger, molecules, planets, you, emerges from those basic rules.
Okay, then what are you exactly talking about? Like, uh, how particles actually combine and how they interact?
At the smallest scale, particles combine and interact via fundamental forces. Quarks, for instance, bind to form protons and neutrons via the strong force. Electromagnetic interactions govern how electrons orbit nuclei, forming atoms. The weak force allows particles to change type, which is crucial in radioactive decay, and the Higgs field gives particles mass. Each interaction is governed by a force carrier, gluons for the strong force, photons for electromagnetism, and so on. So all the complexity around us boils down to these fundamental particles and their interactions.
So in the universe, what exactly it is made of? Also, sun is the only source of photon.
The universe is made up of fundamental particles and forces. At the most basic level, matter is built from quarks and leptons like electrons, and they interact via the fundamental forces. Most of the visible matter we know, like stars, planets, and us, is made of atoms, which are composed of protons, neutrons, and electrons. There's also dark matter and dark energy, which we know exist but haven't fully understood yet. As for photons, the sun is a major source of photons in our solar system. Those photons are what we experience as sunlight. But photons are everywhere. They're produced by countless stars across the universe, by cosmic events, and even from the afterglow of the Big Bang.
So, when we observe such a cosmic event through our telescope in the Earth, so what's the exact date and time that they have happened and we have captured it? It's basically maybe very different because of the speed of light part and the human body incapabilities.
Exactly. When we observe distant cosmic events, like a star exploding as a supernova, we're seeing light that's traveled for many years, sometimes even billions. Because light has a finite speed, what we see now is really a snapshot of the past. If a galaxy is a million light years away, we see it as it was a million years ago. So the date we see the event is actually its ancient past. Our human limitations, our short lifespans, mean we can't directly experience the original moment. Instead, telescopes let us collect these ancient messengers of light, showing us the universe's history.
What do you mean by this distant cosmic event?
I mean any large scale event out there in the cosmos. Things like a star going supernova, two black holes merging and sending out gravitational waves, or a distant galaxy forming new stars. These are grand events on astronomical scales. Because the universe is vast, Light or other signals from these events can take years, centuries, or even billions of years to reach us. In other words, we're observing events that happen far away, not just in space, but also in time.
What do you mean by that space and time part?
When I say space and time, I mean that the universe is so vast that distance and time are linked. Light, which travels at a finite speed, takes time to cross space. When we look at something far away, we're seeing it as it was when the light left it. So space, distance, translates directly into time, the past. If a galaxy is millions of light years away, its light took millions of years to get here. So the farther out in space we look, the farther back in time we're seeing.
Suppose the telescope would only collect the information as a source of photon only now, like whatever it reaches and take the snapshot, and based on that snapshot, it tells us exact information.
Exactly. That's what most telescopes are doing. They gather photons that have traveled from distant objects, stars, galaxies, cosmic events. Each photon carries information, its energy, its wavelength, and its direction. By collecting many photons, we build up a picture, a snapshot of what that object looked like when those photons were emitted. By analyzing the light, its spectrum, shifts in wavelength, brightness, we infer temperature, composition, motion, and even how far back in time we're looking. So that snapshot is the light story telling us about the past.
So you have to give an example to support your story that you are talking about, that each photon carry information, its energy, wavelength, and its direction. Collecting many photons, we can build picture snapshot of what the object actually looked like when this photon were emitted. By analyzing this light spectrum, shift in wavelength, brightness, infer temperature, composition, motion.
Sure, let's take the famous example of a supernova when a massive star explodes. When astronomers detect supernova light, each photon has a wavelength. From that, we figure out what elements are present, like hydrogen or iron, because each element emits a distinct pattern of wavelengths. The brightness tells us how far away it is. If the light is stretched, redshifted, we know the supernova is receding due to the universe expanding. By analyzing many photons, we reconstruct when it happened, how massive the star was, what elements it made, and how it's moving. In this way, the photons become a story, letting us piece together that ancient stellar explosion.
So, what are the things we can discuss next about the standard model of particle physics?
We can dive into whichever part intrigues you. Maybe we can talk about how the Higgs field gives mass to particles, or how quarks are never found alone due to confinement. Or we could delve into why gravity isn't included in the standard model. What's sparking your curiosity next?
Okay, then exactly.
Whenever you're ready, we'll pick up from there. The standard model's got plenty of corners to explore, and we can take them one step at a time.
So, what are the actual uh, particle inside the standard model that they discuss, and exactly where they found?
The standard model has two main families of matter particles, quarks and leptons. Quarks come in six types: up, down, charm, strange, top, bottom, and are found inside protons and neutrons. Leptons include the electron, muon, tau, and their neutrinos. Electrons orbit atoms, while neutrinos rarely interact. Force carriers include photons for electromagnetism, gluons for the strong force inside nuclei, and W and Z bosons for the weak force, which changes particles. And the Higgs boson gives particles mass. All these particles are found in every bit of matter around us, from the smallest atoms to the largest stars.
So, there might be quarks, leptons, outside
Yes.
our Earth that may be same within inside our Earth?
In a sense, yes, all matter around us is made of the same fundamental particles. The quarks and electrons inside you are the same kinds found in distant stars. The difference is how many and how they're arranged. The atoms in your body, in planets, or in galaxies, they're all built from the same building blocks of the Standard Model. It's quite amazing. We're literally made of the same stuff as the stars.
So can we build a actual human body by making a right composition of this elementary particle?
In theory, if you had the exact arrangement of all the atoms and molecules that make up a human, you could replicate the physical structure. But it's unimaginably complex. Life isn't just particles, it's how they interact, self-replicate, and are shaped by information encoded in DNA. So while the Standard Model particles form everything, life is about intricate organization. We aren't anywhere close to assembling a living being from scratch. Nature's recipe is far more intricate than just mixing particles.
Okay, do we discuss a very useless thing here?
Not at all. It's natural to ponder these things. Wondering if we could build life from fundamental particles helps us appreciate how intricate life truly is. Understanding that we're made from the same particles as stars is a humbling realization. These questions bridge science and curiosity, and that's never useless.
So for the stars part, there might be a chemical reaction happening so that they produce this fundamental particle, or maybe some stars are made of a fundamental particle.
Stars don't produce fundamental particles from scratch. Instead, stars are made of these fundamental particles, mostly hydrogen and helium atoms, which are built from quarks and electrons. Inside a star's core, nuclear fusion happens. That's where lighter nuclei like hydrogen fuse into heavier ones like helium, releasing energy. But the particles themselves, quarks, electrons, neutrinos, are fundamental. They existed since the early universe. Stars just rearrange them into heavier elements.